Hello, welcome to 13.2, which is the second part of HL Periodicity. So in the last video, there was a bunch of stuff where I said I'm going to talk about that more in the next video. This is that video. So here's what we're going to be discussing. We're going to be talking about orbital splitting, and we're going to talk about coloured complexes, that the colour absorbed is complementary, and we're going to link this splitting, which is these two guys, into why these are different colours and why different ligands produce different colours. Please note, you're not expected to know the colour of particular complex ions. All right. So shapes of complexes. So how we define a shape of a complex. So last video I sketched this in the middle where I had my metal ion in the middle. So the IB only expects you to know about octahedral complexes. So these are where you've got your ligands around and they form an octahedron. So the IB only expects you to talk about octahedral complexes. However, there are other shapes of complexes, so you can have linear and you can have what's called square planar. So as the name suggests, linear is in a line, and I'm just using L to indicate a ligand here. And then square planar, which is all four ligands in a flat square shape. But it's this octahedral that the IB expect you to know. The complexes that the IB always talk about are these octahedral complexes. Okay, so I drew a quick version of this on the last one, but let's do this quickly. So in what is called the free ion, which I'm going to draw in red, all 5 of my d orbitals have the same energy. But as a ligand approaches, sorry, I'm just trying to work out what pen color I want to use. But as my ligand approaches, what happens is my orbitals split. So I end up with 2 with slightly higher energy and 3 with slightly lower energy. And it would be good if I could draw those so they were vaguely on top of each other. Now, what that means is that if I've got an electron in the lower part, it can absorb light and jump to that higher split orbital. Sorry. So if I plus energy, I can move that electron up from the lower orbital to the higher orbital. Now, because these energy levels are so close together, this energy that I'm adding is in the visible spectrum. So it's this orbital splitting because my ligands are approaching. Now, the amount of splitting, how far apart these two energy levels are, is dependent on what my ligand is. Depending on how strong, quote unquote, my ligand is, there might be more or less splitting here. So the bigger the split, the more energy I need to add, the higher up the visible spectrum it is. If it's a quote-unquote weak ligand, my orbitals aren't going to be so far apart. The energy I need to add is lower, which means it would be a redder colour on my visible spectrum. So this is directly out of the data book, and what it's basically saying is iodine versus the cyanide ion. Sorry, that's cyanate, I think. Sorry, my brain's not working just at the moment. That is saying that the energy difference for my iodide ion is much lower than the energy difference for my cyan, whatever that is. So the energies required for me to move my electron from one to the other is different because this ligand has a different quote-unquote strength to it. There are some other things that affect the colours of these. One of them is the identity of that metal ion I've got. Obviously different metals, because they've got different core charges, they will have different amounts of quote-unquote attractive power. The oxidation state, because if you remember from our discussion of discontinuities in ionization energies, moving an electron out of a paired orbital is going to be harder than moving an electron out of a single orbital and a single occupancy, and that's because, and that can be affected by oxidation state. Cool, let's continue on to discuss some other ligands. So all of the other ligands we looked at, and I'm just grabbing those two as examples, these are called monodentate. So dentate, you're like, what's this about teeth? Think of these as taking one bite out of that metal ion. They've got one tooth that they're attaching to that metal ion with. Something like EDTA, though, is what is called hexadentate. There are 6 points of contact between our EDTA and the metal. So if you think about that ligand, EDTA basically wraps around the entire metal ion. EDTA is actually a pretty useful, I was going to say metal detector, but a pretty useful indicator for metal ions. Something like ethandiamine, if in doubt, go back to go back to intermolecular forces. You've got something that is positively charged in the middle. So your ligands are going to need to be either negatively charged, like these monodentate guys, or they're going to need to have nice chunky lone pairs of electrons to attach onto our metal ion. So this is bidentate, because it's taking 2 bites out of our metal ion. Ethanedioate is also bidentate. All right, let's continue. Okay, so these diagrams are both out of the data book, and I've added this electromagnetic spectrum just to give you this sort of zoomed out version of that color wheel. So where the colors of these transition metal complexes come from, think about our orbitals. So if I only need to add a small amount of energy to move up from my lower to my higher, look at that on the color wheel. If I'm absorbing reddish light, what's going to be left over? Light is characterized by subtraction. So we start with white light coming from the sun. If this particular metal complex is absorbing the red, I'm going to end up with something that's greenish. You look opposite on the color wheel. So for example, I said in the last video that iron, one of the oxidation states of iron, had a particularly pretty pale green color. So that's because it's absorbing red light. Now, so it is green, which means it's absorbing red light, which means that there isn't much splitting in those d orbitals. So when we look at something that has very high splitting, and again, I know I haven't drawn those remotely on top of each other, I have quite a lot of energy that's needed to move my electron from here to here, which means that it's absorbing purple. Therefore, large splitting. Therefore, absorbing purple. Therefore, orange is going to be transmitted. It's like, imagine these things with light are like sharing a packet of jelly beans with me. I'm one of those strange people who loves the licorice jelly beans. So if you see a packet of jelly beans, like around my parents' house, because I can't buy them for myself, because I'd eat them all. If there is like a container of jelly beans at my parents' house and all of the black ones have been picked out, you know I've been there. The same thing goes with these metal ions. If there's particular wavelengths missing, they can correspond to these particular energy transitions, which means that you can identify what metal is there by what wavelengths are missing. Just like you can identify if I've been at my parents' house because the black jelly beans are missing. Okay. I know the jelly bean metaphor is a bit of a stretch, but that's how I personally make sense of it. Okay, so this was quite a quick video, but let's just quickly go through and talk about what we talked about. Go through and list what we talked about. We talked about splitting, and we talked about light being absorbed as the electron gets moved between those levels. We talked about colour absorbed being complementary to the colour observed. We talked about identity of the metal ion, oxidation number, and identity of ligand and the effect that they have on colours. We talked about different ligands on splitting and using the spectrochemical series. The spectrochemical series is given Polydentate ligands are given, and you're not expected to recall the color of specific complex ions. Okay, thank you so much. Have a fantastic rest of your day, and I will see you next time. Bye.